Hi guys, good day. My report is all about grain size analysis of soil, including both mechanical and hydrometer analysis. So let's start. What is mechanical analysis of soil? It's the determination of the size range of particles present in a soil, expressed as a percentage of the total dry weight. There are two methods generally used to find the particle size distribution of soil. Number one is sieve analysis. Sieve analysis for particle size is larger than 0.075 mm in diameter. And two, hydrometer analysis. Hydrometer analysis for particle sizes smaller than 0.075 mm in diameter. The basic principles of sieve analysis and hydrometer ever analysis are briefly described in the following two sections. Sieve analysis consists of shaking the soil sample through a set of shapes that have progressively smaller openings. Table 1 lists the US standard sieve numbers and the sizes of openings. First, the soil is oven dried and then all lumps are broken into small particles before they are passed through the sieves. Figure 1 shows a set of sieves in a sieve shaker used for conducting the test in the laboratory. After the completion of the shaking period, the mass of soil retained on each sieve is determined. When cohesive soils are analyzed, it may be difficult to break lumps into individual particles. In that case, the soil may be mixed with water to make a slurry and then washed through the sieves. Portions retained on each sieve are collected separately and oven dried before the mass retained on each sieve is measured. The results of sieve analysis are generally expressed in terms of the percentage of the total weight of soil that passed through the different sieves. Table 2 shows an example of the calculations required in a sieve analysis. So this is the sets of sieves in a sieve shaker. So let's proceed to hydrometer analysis. Hydrometer analysis is based on the principle of sedimentation of soil grains in water. When a soil specimen is dispersed in water, the particles settle at different velocities, depending on their shape, size, weight, and viscosity of the water. For simplicity, it is assumed that all the soil particles are spheres. Particle size distribution curve. The results of mechanical analysis, sieve, and hydrometer analysis are generally presented by semi-logarithmic plots known as particle size. Diameters are plotted in the log scale, and the corresponding percent finer in arithmetic scale. As an example, the particle size distribution curves for two soils are shown. The particle size distribution curve for soil A in the combination of the sieve analysis result presented in Table 2 and the results of the hydrometer analysis for the final fraction. When the results of sieve analysis and hydrometer analysis are combined, a discontinuity generally occurs in the range where there are overlap. This is because soil particles are generally irregular in shape. Sieve analysis gives the intermediate dimension of a particle. Hydrometer analysis gives the diameter of a sphere that would settle at the same rate as the soil. The percentage of gravel, sand, silt, and clay size particles present in a soil can be obtained from the particle size distribution. The percentage of gravel, sand, silt, and clay size particles present in a soil can be obtained from the particle size distribution curve according to the Unified Soil Classification. Soil A in Figure 2 has gravel size limit minus greater than 4.75 mm is equals to 0%. Sand size limit 4.75 to 0.75 mm is equals to percent finer than 4.75 mm diameter minus percent finer than 0.075 mm diameter. is equals to 100 minus 62 minus 38%. Silt and clay. Size limit less than 0.075 mm is equals to 62%. So let's proceed to example number 1. The table shows the laboratory results of the sheave analysis of a sample. Plot the grain size curve of the soil in the chart. Determine the following. A. Determine the nearest value of the effective size. B. Determine the nearest value of the coefficient of uniformity. C. Classify the soil according to the unified classification system. Solution. Letter A. Effective size. The effective size, diameter 10, is the diameter of the particle of which 10% of the soil is finer. Diameter 10 is an important value in irregular flow of the soils and can significantly influence the mechanical behavior of the soil. Diameter 10 is equals to 0.149 mm. Letter B. Coefficient of uniformity. Diameter 60 is equals to 2.22 mm. Diameter 10 is equals to 0.149 mm. So let's substitute. Diameter 60 is over diameter 10 is equals to 2.2 over 0.149. The answer is 14.77 mm. Letter C. Coefficient of curvature. Diameter 30 squared over diameter 10 times diameter 60. So let's substitute. 0.63 squared over 0.149 times 2.2 is equals to 1.21 mm. Since the curvature is greater than 6, coefficient of uniformity is between 143. The soil is well-graded sand. This is the grain size distribution subgrade. Example number 2. Classify the following by using the USDA textural classification system. The soil has a particle size distribution of 20% gravel, 10% sand, 30% silt, and 40% clay. A. Compute the percentage of sand. Letter B. Compute the percentage of silt. Letter C. Compute the percentage of clay. Letter D. Classify the type of soil. Solution. 0% sand is equals to 10 over 100 minus 20 times 100% is equals to 12.5%. Letter B. Percent of silt. 30 over 100 minus 20 times 100% is equals to 37.5%. Letter C. Percent of clay. 40 over 100 minus 20 times 100% is equals to 50%. The classification of soil is clay.